Hi, welcome to Mathematics with Tom. This is Tom, and today we're going to take a look at two more examples in the study of vector spaces. And the first one is the plane spanned by the vectors. How about we'll use the vectors 1, 1, 0 and the vector of 1, 3, 0. So that's the first one. So I'm gonna do my best. I'm gonna see if I can. Let's undo those last mistakes. Okay. So here's what it looks like. I'm gonna try to sketch this. Actually, I'm gonna sketch this. Okay. So the vector, and let's put our tick marks. Here's 1, 2, 3 on the x-axis. And then on the y-axis, we have the similar ones. We're going to have a 1, 2, 3. Maybe we'll even go to 4. I'm not sure what we're going to need exactly here. And then on the z-axis, we'll go 1, 2, 3, 4. All right, so there are my three axes. And let's graph these. So we'll use orange then for our first one. So the vector 1, 1, 0 is this vector right out here. It's in the xy plane. And we'll call that vector x. And I'm going to call 1, 3, 0. We'll call that our vector y. So x is 1, y is 3. Oops, kind of got off there. So this is my plane spanned by x and y. And so what is the plane spanned by x and y? It's just the xy plane itself. So it's all of this. If you wanted, we could do like cross-hatching like that. So it's just this flat. You could almost think of it like as the floor in a room. Now, well, the plane is just a set of all possible linear combinations. So that is, a plane is a subspace. Let's draw another subspace that I know we know well. We'll call this one L. L, let's go back to my white marker here. So, and I'm going to call the plane spanned by x and y. So we'll call plane spanned by x and y. This will be the vector space P. And then the vector space L is the span. It's the span of, let's call it z. We'll call it the vector z. And it'll have components of 0, 2, 2. 0, 2, 2. Let's try that. Okay. And let's graph z. Let's see what let's do as a different color entirely here. We'll use this nice red. Oh, how about this pretty pink? Now, remember the L is the span of z. Well, that just means take z and multiply it by all possible scalars. Well, so that means if I go x is 0, y is 2, z is 2. There's my vector right here. There's my vector. And so then this is just the line that continues up to the right. And if you could see down below the picture, it would be going off underneath the floor down into there. So this is L. This is my vector space L. And the green one here is my vector space P. Now, here's my question to you. Here's my question. For this question, let's go back to white. Is the union, so is P union, that's a big union, L a subspace? Question mark. Okay, Well, if you recall, we have our three conditions. So let's do this. The very first one is we have to say, well, is the 0 vector in P union L? And the answer is very clear, because they are both, one's a plane and one's a line, and they both go through the origin. And so we would say yes. Okay? Or we could make a linear combination of vectors with scalars 0, and we would be at 0. Now, let's try again. The second one says that if I take the span of P, well, the span of P would be some C times X plus some D times Y plus, let's take a E times Z. And the question is if that is in P union L. Now, let's just try. I'm kind of curious. Let's just get a feel for this. What if I just take a C equals D equals E equals 1? Let's see what happens. All right, so then that's going to be the vector 1, 1, 0 plus the vector of 1, 3, 0 for Y. I should write it that way. We're going to take X, and we're going to add it to Y, and we're going to add it to Z. So plus Z is 0, 2, 2. Now if I add those together, this gives me the vector of 2, 4, 5, 6, 2. 2, 6, 2. Or I could also think of it, it's going to be all the possible scalars of the vector. So it's going to be 2 times, what would that be in this case? 1, 2, 1. So let me just see if I can graph 1, 2, 1. I'm going to graph 1, 2, 1. So X comes out 1. Then I go over 2 units in the Y direction. So I go to here. Probably run out of good colors. Maybe gray will show. So 1 on the X, 2 on the Y. So I'm coming out to 2 on the Y. And then I have to go 1 up into the Z's. Well, what does that mean? That means that my vector is this gray dot right here. But wait a minute, what happened with that gray dot? That gray vector, this is the sum. We'll call this W. W is not in L, nor, let's call it nor is W in P. It failed the closure property. By adding something from the plane to something from the line, we ended up with something that I don't know how else to say it, but something that literally popped out of the space. The space itself is not closed, we would say. So because it's not closed, P union L, so there we go. So P union L is not a subspace. And we're in R3, so we could even be more specific. We could say it's not a sub. I knew that something in that word just was not going to lend itself to working very well. It's not a subspace of R3. Now, let's try this. The intersection. What about P? What about what about P intersected with L? Meaning, what do they share? What do they share in common? Well, the answer is already on our board here. The answer is this red dot. Let's go back to that red dot down there. That red dot was the one thing that was both in P and L at the same time. That red dot is the 0 vector in R3. So let's see. Is the 0 vector a subspace? Is it a subspace? That would be our next natural question. So to do that, I'm going to scroll down. Let's get a new piece of paper and see if we can find out, is 0 a subspace? Okay, here we go. Is 0 vector a subspace? Okay, here we go. So the first thing we have to do is we have to say 1. Well, is 0 vector in P intersect L? Well, yes. That's the one thing they do have, is they do have the 0 vector. So that first one is satisfied. The second one, now the second one says that if we take x, some vector x and some vector y that are in the 0 space, the 0 vector, then x plus y has to also be in that space. So let's try that. Well, this is going to seem kind of funny, but what is in the 0 vector space? 0. So if I take the 0 vector for x, and if I take another thing that's in the 0 space, well, that's 0. That's the only thing in there. And I add it to itself, what do I get? I get the 0 vector again. In other words, it's closed under addition. So we would say, so this worked. It's closed by vector addition. Now, the next one is this. So the next one is 3. Of course, that follows 2, right? So the next one is, if I take any scalar c in the real numbers, and the question then is c times the 0 vector, is it still in the 0 space? Well, it's pretty clear that if I take c and I multiply it by 0, 0, 0, I get 0, 0, 0. So I'm back at the 0 vector. And in fact, the 0 vector is a subspace. It's a subspace of R3. There's one in R2 and R4 and even in Rn. And you may have recalled from our previous videos, we already said that. So the 0, we said the 0 subspace, did it again. 0 subspace is denoted as, and we use this capital Z, and it's not the Z for the integers, it's just a capital Z. So there you go. Those are 2 more examples of subspaces, and I hope that helps. Thanks for watching.